Hello everyone, I am Taisei Miura in Kogakuin University in Japan. I'd like to talk about cache replacement based on LSTM in the second cache in virtualized environment. This is the outline. First is background. Virtualized environments have become one of the most important platforms for cloud computing systems. Storage access from applications in host type or hypervisor type virtualized environments is executed via two caches. The first one is a cache in the guest OS. The second one is a cache in the host OS. Therefore, improvements of the hit ratio of both OS caches are important to improve the I/O performance. Next is related work. This is cache replacement in the second cache. LRU has been widely used for cache replacement in the system software field. However, this replacement algorithm does not work well in the second cache, which is the cache of the host OS in the virtualized environment. This is controlling the first cache. For improving the second cache hit ratio. In this method, the guest OS cache keeps fixed state by discarding the other date. Then, it improves the reference locality in the host OS cache. This method discards the other date using the f-advice system call of Linux. Next is proposed method. We propose a cache replacement method based on LSTM, which is one of deep learning methods. The proposed method creates a storage access predictor with LSTM and replaces the cache based on its prediction. This is the LSTM predictor. The predictive models are built by running the storage access history. The history is a set of one-hot vectors that represent the sequence of blocks accesses. Each one-hot vector represents one access. Each one-hot vector is input into the LSTM network. The LSTM network outputs a vector that indicates the probability of access of each block in the next access. Implementation. We implemented cache replacement of the proposed method using the f-advice system call. When the storage is accessed, the accessed block is provided to the predictor. Then, the predictor predicts the next access block. Then, the method issues f-advice system calls to the blocks for the k blocks with high probabilities. K is determined by this equation. CLSTM is the size of the cache. Next is evaluation. We evaluated the I/O performance of LRU and the proposed method using a simulation and our implementation. We report the I/O requests in an access log published in SNIA and then measured their I/O performances. Because the storage size of the log is huge, we managed the access log with 1 GB blocks. This is the experimental setup. The number of the requests in the access log is around 83,000. The number of blocks is about 10,000. The size of the LSTM is 4,800 megabytes. Host OS cache size is 4 gigabytes. These are the parameters of the constructed LSTM model. The numbers of dimensions of input and output vectors are about 10,000. The number of the middle layers is 1. The number of dimensions of the layers is 100. The activation function is a rel function in the middle layer. It is the softmax function in the output layer. The optimization function is the attempt function. The loss function is the softmax cross entropy function. This figure shows the relationship between the temporal distance of the axes and the frequencies of the log. This shows that there is strong locality. In other words, there are many axes with short time distances. First evaluation is the cache hit ratio evaluation by simulation. We evaluated the cache hit ratios in a two-cache environment. The host OS cache size was 400 blocks. The guest OS cache size ranged from 100 to 1000 blocks. I/O accesses were issued in the guest OS. Accesses that missed the guest OS cache were transmitted to the host OS cache. This is the result of cached simulation. The blue line is the LRU. The orange line is the proposed method. In the most cases, the proposed method outperforms the LRU. In the cases in the red circle, the cache hit ratio improved by about 10%. In this case, the effect of the guest OS cache was very small. In such a case, the LRU worked well as usual. Next is the I/O throughput evaluation. Accesses to the host OS cache. We replayed the senior's access log and emulated the guest OS cache using LRU. Accesses that missed this cache were issued in the host OS. We separated the storage area of the log with 1 GB blocks, and we issued 10 MB I/O requests in the physical computer instead of 1 GB block in the log. We measured the throughput of these I/O requests. This is the result. The blue line is the LRU. The orange line is the proposed method. We can see that the proposed method outperformed in all the cases in this graph. That is, from 160 to 1000. In the case of 240 blocks, the throughput improved by 4.7%. This is a summary of the evaluation. The simulation results show that the cache hit ratio of the proposed method was better than the traditional LRU. The proposed method achieved about 10% cache hit ratio, even when the ratio of the LRU was almost 0%. The method also showed a better performance than LRU in the I/O throughput evaluation. It improved by 4.7% at most. Finally, the conclusion. We proposed a cache replacement method using LSTM in a virtualized environment. The performance of the proposed method was evaluated by simulation and experiment using published storage access logs. Both of simulation and experimental results showed that the proposed method achieved the better performance than LRU. Thank you for your attention.